Perpendicular bisectors. In just a bit, we're going to look at this as a segment within a triangle, but right now we're going to start with just defining it independently. A line, a ray, a segment, or even a plane that is perpendicular to a segment at its midpoint is a perpendicular bisector. All right, so the picture that we have here, it begins with a segment. It's sort of important that we know what we start with first. We start with a segment that would be AB, okay, a well-defined segment. It has a link to it. Okay, and that has a midpoint, which would be at point P here. All right, and any line, ray, segment, or plane, so even a plane, if we're doing this in three-dimensional space, any of those items that pass through P would be called a bisector, would be called a bisector. Now, if they go through at P to make a right angle, we get to call that a perpendicular bisector. All right, perpendicular bisectors have a property that I would like to demonstrate to you. And to do that, I'm going to use a piece of patty paper, which is also just called tracing paper. Okay, so it might be a little bit hard to see it, but I've got a little thin piece of paper here. What I'm going to do is start with a segment. I'm just going to start with a segment. All right, and I'm going to make the endpoints of that as well defined as I can. We'll go ahead and call them A and B. Sort of matches what we see there. All right, now what I need to do to get a perpendicular bisector is identify a midpoint. I got to get a midpoint, and instead of measuring this time, what I'm going to do is actually just fold this over. Okay, I'm going to fold it over so that point B ends up on A. And if you do that, the lines are going to automatically match up. Okay, they're going to match with each other, and I'm going to make a crease right here. Okay, so that identifies a midpoint. I'll go ahead and just call that P to match the other picture that I got there. All right, that is a midpoint. So I'm going to go ahead and add those markings there. And the neat thing about how I did this, right, I didn't measure it and then mark it off. I actually folded it. The neat thing about it when I folded it is that that crease is actually perpendicular. It's a perpendicular crease. And we can sort of verify that by just folding it back together here. If I do that, right here, that piece, it matches, you know, the paper that's underneath it on the other side. All right, so if I highlight that crease, what I'm looking at is this angle here matches that angle. And the only way that's going to work out, being that these are linear pairs, that they would each have to be 90 degrees. All right, so with that fold, I automatically get my perpendicular bisector. All right, so here's the property. If I identify any point that would be on the perpendicular bisector, there's something true about that point. All right, what do you think that is? What do you think is true about point C? Here's what's true about point C and any other point that would be on this segment, including, let's just go ahead and put a point D right there just to show it. Any point that would be on here, what's true about it, that point is going to be equidistant. It's going to be equidistant to the endpoints. Go ahead and draw a segment connecting. All right, so how do we know that's true? Well, if I fold it back together, you're going to notice that those two segments match up, which is the definition of being congruent. They are the same length. These are congruent to each other. Now, the same thing would be true with D. Okay, that'd be true with D. For this, let's go ahead and just do dashed lines. Make those look a little different. All right, now fold together. And you'll notice that the dashed lines match up. All right, so any point that is on the perpendicular bisector is going to be equidistant from the endpoints. All right, now all of that approach is actually inductive. I just built this using patty paper. Everything seems to work out, but it is technically an inductive approach. We can, however, very easily do a deductive proof. We could write a two-column proof to do this. Now, we're not going to write it, but we're just going to at least look at what would be true. All right, so things that we would know. AP is going to be congruent to PB, right? So if this is defined as a perpendicular bisector, we get two things. We get the bisecting, which means that AP is equal to PB, We also get the right angle that we have here, which means you got a right angle over there. All right, so I'm going to start thinking this as two triangles. The left and the right, they both have that segment, they both have a right angle, and in addition to that, they have a shared side right here. They have a shared side reflexive property. So by side angle side, I can actually prove that the two triangles are congruent. I'll at least write that. Side angle side is going to prove that these are congruent. And then, because CP, corresponding parts of congruent triangles are congruent, because of that, AC has to be congruent to BC. And that would be true, of course, for the bottom part as well. All right, let's officially state our perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant. It is equidistant from the endpoints of the segments. All right, so for example number 1, we're asked to find AD, the length from A to D, which is being described here as 5x. That means we need to figure out what x is. All right, we're going to figure out what AD is if BD, that's right here, if that were a perpendicular bisector of AC. Okay, so as a perpendicular bisector, you've got congruences there. We also have our perpendicular there. All right, so D is the point that's on the perpendicular bisector. It will be equidistant from the endpoints of the segment AC that it is bisecting. That means that 3x plus 14 is going to be equal to 5x. We'll subtract 3x. 14 equals 2x. Divide by 2, and x is equal to 7. All right, so the length of AD is going to be 7 plugged into that spot, which will give you 35. And of course, you could plug the 7 in here, get 21 plus 14, which is also 35. All right, the fun part, perpendicular bisectors of the sides of triangles. We're going to look at that in just a second. But before I do that, I need to define a couple things real quick here. When 3 or more lines intersect at the same point, they are called concurrent lines. And the point of intersection is called the point of concurrency. All right, so down here I got a few diagrams. And in those diagrams, there's a lot of stuff there. But what I want to point out is that there's a point P in each of these. There's a point P, and that's going to be a point of concurrency. There's 3 lines that are all intersecting at that spot. So the lines are called concurrent lines, and they all meet at this unique place right here, which we're going to call a point of concurrency. All right, so I have a piece of patty paper here, and what I'm going to do is draw a picture of a triangle. My attempt when I do this is to not get any special type of a triangle, not aim for an isosceles or equilateral. Okay, if you can be unique, that would be neat. All right, so I got a picture of a triangle, and what I'm gonna do next is identify the perpendicular bisectors of all the sides. Okay, let me start with this one. Let's call it AB. All right, so the perpendicular bisector to AB. What I can do for this, since I'm using patty paper, I can actually just fold it over and make a crease. All right, and then that crease, this is gonna get a little confusing because there'll be a lot of lines, but I'm gonna go ahead and highlight that. I'll put a little right angle. I think that'll help out there. This is congruent to that one. We might get a lot of markings in here, but all that is true. This is a perpendicular bisector AB. Notice it does not go through the vertex that was up here, right? I didn't use an isosceles triangle, so we don't get special cases like that where that vertex would be on that bisector. I wanted it to be unique. All right, let's take this side. We'll call that C. All right, fold that over again. Make a crease. Going to highlight that crease. Like that. I'll go ahead and put some double markings, right angle, and that is a perpendicular bisector as well. Last, we got CA. I'm gonna do that one as well. All right, take a look at the picture real quick though. Something neat is gonna happen here. All right, I'm gonna take A and fold it over to C. And I'm gonna match them up. I'm gonna make a crease. All right, when I open it up, that crease that I just made here, that perpendicular bisector is going to intersect at the exact same place that the other two did. And that's congruent, that is a right angle. All right, so the perpendicular bisectors of any triangle will end up being concurrent lines, and they will find a point of concurrency. They'll find a point of concurrency, this point here. All right, now what's really interesting about that point though, not just the fact that all these meet at that spot, that's pretty cool on its own, that they all end up meeting at this spot, which in my picture ended up on the outside of the triangle. That's cool. What's really neat about that is if we take our perpendicular bisectors theorem, it talks about being equidistant. That point has to be equidistant from C and A because it's a perpendicular bisector, right? It has to be equidistant from C and A. But it also has to be equidistant from B and C. And it also has to be equidistant from A and B. That point has to be equidistant from all of those points. So what that means is we could take a compass. We can take a compass and center it at the point of concurrency, measure out to any point. Okay, so I'm measuring out to C, and we could draw a circle that goes through all of the points. I missed that one just slightly. Got caught on my paper there. All right, but I could make a full circle. Let me see if I can do the rest of it. Let me see if I can fix it up here. It's barely gonna make it. Rotate a little bit more. All right, there it is. All right, that point is equidistant from all the endpoints of the side links that we have there, which means that we can build a circle that goes around that triangle. We say that the circle circumscribes the triangle, or we can say that the triangle is inscribed into the circle. All right, so let's go back to those pictures I had earlier. We actually got 3 cases with the point of concurrency of perpendicular bisectors. We have 3 cases. The one that I ended up demonstrating was this last one over here. You can end up with a point of concurrency outside of your triangle if you had an obtuse triangle. All right, so if I went back to my picture, it ends up that this is an obtuse angle here. Let's grab a protractor just to briefly kind of show it, but it's going to be past 90 degrees. Might be difficult with all the lines are shown here, but that is just slightly obtuse. So I ended up with a point of concurrency that was outside of my triangle. You could end up with a point of concurrency on the triangle if you actually have a right triangle. That one's pretty interesting. And if you have an acute triangle, okay, no right angles, no obtuse angles, your point of concurrency ends up inside of the triangle. But in every one of the pictures, that point of concurrency is going to circumscribe the triangle. It's going to go around it. It doesn't matter what type of triangle you have, this will always work. All right, this point of concurrency does have a name, which is the circumcenter. Okay, and that's because the circle will circumscribe that triangle. So we call this the circumcenter.
Later, blah.